My name is Elena Kolevska. I hope this is working now. Yeah. My name is Elena Kolevska. I'm your neighbor from Macedonia, although I don't live there for a long time now. And today we are going to be talking about Redis. First, let's go with a really short info. I'm sure most of you know what is Redis. Who here has worked before with Redis, at least basic caching? Okay. And how about using more advanced, the other data structures? Like anything else about but strings? Okay. Okay, good. Redis is basically a database, in-memory data store, open source, used mostly as cache, but also can be used as many other different things, as we are going to see in our examples in a bit. I'm not saying key value store, which is a very common description for Redis, because it's not plain key value store. It's more like it's more like data structure, because it has different data structures. Some other basic features of Redis are it has keys with limited time to live, so we can set expiration dates. And differently from memcached, Redis is able, I'm mixing languages, I'm so sorry. Redis is able to expire keys that are not getting accessed. So Redis has a mechanism to actively expire keys that haven't been accessed, differently from memcached. In memcached, if you have a key that already expired, but your code never accessed it ever again, it's going to just stay there in memory and keep up space. With Redis, that's not the case. That thing is handled. Then we have Lua scripting. So there is the option to execute code inside of Redis itself, to execute logic inside of the Redis server itself. We are going to see an example of that. And when I learned about it, I was blown away. But let's see if I manage to do the same with you. Transactions, so atomic operations. We have pipelining to save up on network requests. I'm going to explain that in detail also later. There is also a PubSub server. From the DevOps perspective, there is built-in replication, clusters, different levels of on-disk persistence, and my favorite feature of all is speed. Redis is famous for that. There are available clients in almost all languages. In PHP, there are the two usual extensions. The two most common ones are PHP Redis and pRedis. I usually work with pRedis, and our examples that we are going to see are going to be in pRedis. I mentioned the different data structures. It's these 7, and we are going to quickly step through them to see how they work, what are they about. The one you're probably familiar with is strings. Can everyone read? I know it's a little bit dark. I don't know if it's OK. So the strings are the most widely used data structure in Redis. Binary safe, so it can be text, it can be even images. I just talked to some people that are using Redis to store even images, and it's working really, really fast. Maximum size is half a gig, differently from memcached. Again, we have a lot more space to work with. And a fun fact, not exactly related to strings, but I put it here anyway. Key names can be emojis. Yeah, conference worth mention, no. OK, so next data structure, lists. Inside of those 512, half a gig, we can have, instead of one string, we have a collection of strings. They're sorted by order of insertion. They can be duplicated. So because they are sorted by order of insertion, they are great for timelines. They are also great for queues. So we can do left pop, right pop, left push, R push from both ends of the queue. And all of those are O1 operations in the big O notation. So it requires constant time. It doesn't depend on the length of this list, which, by the way, can be over 4 billion elements for one list. Then sets. It's similar to lists, also a collection of strings, but here we have unique elements. So elements can't be repeated. If we add multiple times this one same element, we will only see it once in this list. That's what makes, what makes them great for tracking, for example, unique IP addresses from visitors or stuff like that. Max length of this list is, again, over 4 billion elements, and we can do unions, intersections, differences on sets. Hashes is what we usually use when we want to represent objects. There are maps between string fields and string values, as represented here. Yeah, as I said, great for tracking, representing objects. It's interesting. The Redis documentation says that for like small hashes, maybe sometimes it's even more performant to use a hash with, I don't know, less than 100,000 fields. It's more performant to use a hash than different string objects. So instead of having 100,000 string keys, you have a hash with 100,000 fields. We can't. Depends on the, so it depends on what we need. But yes, if the use case supports it, then it can be an option. Sorted sets, similar to hashes, similar to sets, but now to every field we can attach a decimal value, and we can sort by that decimal value. Indirectly, we can sort even by the key, the field name, because so that's like lexical sorting. It's used for auto-completion a lot. When if we populate all the values with the same value, then Redis will sort by the fields. So we can get ranks of certain elements, like give me the rank of field 3. If we order ascending or descending, what is the rank for it? So it's great, for example, for online gaming, for any leaderboard. Very fast access to elements in the middle from any part of the hash, and that's more or less it. We are going to use this in our example, and you're going to get a better notion of how it works. Bitmaps. It's like strings, but you have bit access level to the data, so you can just manipulate just certain bits without taking loading the full data, getting that out of Redis, but you can do it directly with certain commands. You can find the first set or unset bit, get count or off. I've never done it. I've never worked with this. This is just what I know from documentation. But I never had the need for this. But I'm sure it must be interesting and probably useful for people that need to do stuff like that. Hyperlog logs are also very interesting data structure, used a lot in Internet of Things. It handles a lot of data, and it's conceptually similar to sets, because it represents only uniqueness of certain set. But so this is used for estimating cardinality. First of all, it's not completely certain. There is 1% margin of error, and it handles a lot of data. It can estimate the cardinality of huge sets of data using at most 12 kilobytes. And it uses some algorithms that calculate that which save us a lot of memory, but compensating with this 1% of 1% margin of error. So now, let's imagine. We are a company, we are building a startup, and we are going to be offering other companies a service, an option to analyze their customers' feelings, emotions, satisfaction. How are we going to do that? Imagine there are some tweets on our Twitter page. Let's say our hashtag, the hashtag of our company is this, that's company, for example. And we have tweets like that, we have tweets like this. There are like a bunch of tweets people are sending to us. And we would like to know as a company, are those tweets generally positive or negative? So how can we feel that? For example, we could scan for words like love, awesome, hate, or terrible, or frustrated. So we can scan for words like that and just analyze, see the number, the frequency with which those words are appearing. The final dashboard, for those of you who have visual memory, like myself, would be something like this. So we would be showing the total tweets, total number. I would like to say in a certain period, but in this exercise, we're not taking that in mind. We're just going with tweets. Then we are going to show the mainstream of tweets containing our observed hashtags. Substreams, so these are just streams containing some certain tracked keyword. Note, there are hashtags we will be tracking, and then there will be keywords that we'll be analyzing. Hashtags is the stats company or the name of our company. The keywords are love, hate, awesome, terrible, and so on and so on. So we have the substream of tweets per keyword with the total count per keyword, for every keyword. And then in the end, we have the scores. And let's see which word will appear the most. First thing, how are we going to connect to Redis from PHP? I mentioned the Redis extension. Just pull it in with Composer, and it's really simple to connect like this. I'm not going to go into details here. Let's go to more interesting stuff. Let's set the track data. So what do I mean by track data? We need to set, to tell our app which hashtags we want to track and which keywords. We would like to track, for example, the hashtag of our company can be the stats company, or just stats or something. There are multiple. There is not only one. So from this list here, which data structure would we choose? Anyone else has some other idea? Sets. We will choose sets. Collections of unique, unsorted string elements. The same thing also for the observed keywords. These are the commands on the client that we instantiated just a few slides ago. We are going to add. This is the name. Wait, do I have the laser? Yeah, this is the name of the key. And then we specify the hashtags we want to track. For those of you who like to see it visually, it would look probably something like this. We add the hashtags, and we add the keywords. Loved, amazed, frustrated, and so on. Next thing we need to do, we need to somehow get data from Twitter. In this imaginary example, we are using the Twitter real-time API. So when we want to connect it and to tell it which words we need to track, we first need to get those keywords. This is the command to get the hashtags as members. It will return them like this, as an array. Then, when we get the tweet, first of all, this is a conference, so I know many of you would, for example, would say, oh, okay, we don't need like this prefix, we are wasting memory before we go there. This is just I made this stuff just to be more readable for presentation purposes. So let's decide first. When we save the tweets, when we receive the tweets, what are we going to do? We are going to save them first as keys. We will have to do many other things later with them, but let's just start from here now and then think how we are going to process the tweet. Let's form a key name tweet ID, and this is some hypothetical ID from Twitter itself. This is the tweet contents. And which data structure are we going to choose for this?
String in your example.
Yes, because you know the command. Yes, so we are using a string because this is just a simple string. There is no need to complicate more. This is the set command, which sets value to a certain key. Strings, the first one. And then we can process synchronously the tweet to analyze if all the keywords are there or not. But that's probably not very smart, because what if we go down, for example, and we get flushed with a lot of tweets we need to process? Our servers are going down. So that's why we're putting everything in a queue, and then we will be processing as many as we can. So when we receive the tweet, we are going to push its ID to a queue to be processed later. Which data structure are we going to use? You're banned from this game. OK. Yes, we are going to use lists, because as we explained, in lists, we can have repeating elements. They are not ordered by, they are ordered by the order of insertion. So they're perfect for queues in this case. Our key is going to be called message queue. And inside of it, we're just going to be pushing the key names of the tweets. Yes, I'm sorry. It was just there. OK. This is the lists. And then we have now all the tweets in the queue. We need a worker that is going to get stuff from the queue and process them. Let's do that. The command to pop elements from the queue is rpop. So pop of the tail of the queue, and the value, the return value here would be the key name of the tweet. And that's cool, but what if the server goes down or just crashes before we completed the processing of the tweet, and we already popped the element? When we restart everything, that element would be used and would be lost, and the tweet won't be processed. That's why we have the concept of reliable queues. Write pop, L push. So atomically, in just one operation, that is absolutely going to execute. Either it's going to execute or fail, but either way, the tweet ID, the element, will either be in one queue or in the other. What that means? We have a queue of unprocessed elements and a queue for elements that are being processed at the moment, like in process. So in one operation, we are moving the element from one queue to the other. That's the write pop, L push operation. And then we have also blocking operation, blocking left pop, blocking right pop, blocking right pop, L push. What does that mean? So the client connects to the server. It asks, hey, are there any elements for me to process in this list? And the server says, no, I don't have anything. We don't disconnect and come back tomorrow. We wait, we keep the connection open until there are elements in that queue to process, which is, you must admit, much more practical. And in the end, we are going to process, not in the end, but towards the end, close to the end, we have to process the tweet content. Here is the code. This is PHP with Redis. So first we get the tweet contents, we get all the keywords, and then we just loop through the keywords, and we check if the tweet contains any of those keywords. If it does, this is a new command here, that increment by. We are using sorted sets for this. As we said, great for leaderboards. What is this? So in the sorted set, these fields here are going to be the tweet IDs, and these numbers here are going to be the occurrences, well, number of occurrences of those of those keywords. And when we have that data, we can sort as we want. Like we can get the position. What's the position of the word love? It's 5th in frequency. Or give me the top 10, the top most frequent keywords that people are tweeting about us. Something like that. So that's why we are going with sets. Then we are just pushing the tweets to the subfeeds that I mentioned before on the that we need to show on the dashboard. So just a list of tweets containing that certain keyword. We are trimming. This is a new one. We are trimming those subfeeds so we don't overflow them. For example, we just keep 100 elements in the subfeeds. Subfeeds, yeah. In the end, this is also a new command. We increase the total count of tweets, and we also push and trim to the main feed. Then we need to show the stats. Now we have all the data in the database. We need to pull now we need to pull data to show to send to the dashboard. Just to remind ourselves, this is what we want. So we have the mainstream, we have the total tweets, we have the scores over there, the substreams, the count of every substream. This is the code to do it. So to get the total count, we just get the total count. Reverse range by score of the mentioned counter. This is how we get the leaderboard. Feed by keyword, left range, just a range from a list. And feed of these are the subfeeds. No, these are the subfeeds. This is the main feed. Also, they were lists, so we are using the left range command. And this is all very nice. It would work great, but can we make it faster? We can. What would the bottleneck be of this application? Redis is very fast. It can process a lot of data. The bottleneck here would be number of network requests. Redis is a TCP server, and we need to always think in a matter of time. We need to communicate between the client and the server. They're connected with the networking link, and the time from the client to send requests to the server and the server to respond is called round-trip time, and that's something we always need to keep in mind. If we could only somehow lower the number of requests to the server. Let's see where we're at right now. How are we standing with network requests? We're saving the complete tweet. That's a set request to the server. 1. Adding tweet to the main feed, L push, 2 requests, plus the trim, 3 requests. 4. When we get all the monitor keywords, we go to 5 requests. This is logic on the client side only, so no network requests. And then, for every found keyword, we are going to have to do these last 3 commands. That's for every found keyword. Increment, 6. Add tweet, 7, plus the trim, 8. And in the update score, that increment by. That's 9 requests to the server. But what if we find more keywords? That's plus 4 requests for every found keyword in the tweet. So how many network requests per one tweet? No? It's a lot. So there must be a way to do this faster. And there is pipelining. Warp 8. This is how we do it. Redis supports it. It's really simple. So first, we will just have to get the keywords. This is one network request. And then we open a pipeline. Oops, sorry, I'm sorry. And we run all the logic. So this logic of checking if this is shortened code, by the way. I didn't have space to put everything, but all the logic for checking the keywords, if some keywords are part of that tweet, are contained in that tweet or not, is contained inside of this pipe here. How do pipes work? The pipe is opened, and we start sending commands to Redis. Redis starts processing and caching the responses, but it still receives commands from us. And only when we finish sending commands, it will send everything back to us. So responses to many different commands, for set, for push, for trim, all of those, it's going to send us in only one network request. So now we're only down to 2 network requests out of minimum 9 or even more. That's, I think, a very good improvement. But we can do better. Lua scripting. This is the basic Lua script file. Let's just return hello, and this is how we call it from the command line. Pardon. Eval command and path to the script. Let's see how the Lua script for this would look. We're not going to go through all the details. We don't have a lot of time. I want to show some more interesting stuff. But the thing you need to note here is this Redis call. So this is inside of Lua script that is running inside of Redis, is calling this command, Redis call. And here you can see all the commands we already mentioned before. How many network requests are these? Is this? Only one. Only one call to the Lua script. Now, let's see how this is called from the CLI. Just specify the Lua, pass the parameters, pass the contents everywhere, everything the script will need, and that's it. But if we're so worried about network performance, then, of course, someone would ask, but are we going to pass the hello Lua script every time that we're calling, that we want to call it? That's not really optimal, no. So what are we going to do? There is a better way, of course. Redis gives us a way to cache the scripts inside of Redis itself. So the command to do that is script load, and Redis will return a hash, which will be the identifier of that script. Then every time we need to call that script, instead of giving the path to the script and sending the full script text to the server, we just send it the hash. And this is very cool. It could be a little bit tricky to just always maintain all the scripts updated and all the hashes. But I think that's not really that complicated, and it will be worth it. Prepare for Warp 10. Theoretical, I know, but yeah. Modules. What are Redis modules? They're new. It's a new feature. It's a new add-on to Redis. They're written in C. Are there, OK, besides Rasmus, are there any other gods in this room that write C code? Yeah, it's hard. I tried that for the body. That's hard. So they are dynamically loaded libraries, almost as fast as Redis core if we use the low level. I'm going to explain that in a moment. And then they let you extend Redis commands, even create new data structures, access data almost as fast as native Redis commands. The modules API expose 2 levels, high level and low level. And I'm going to explain them now. This beautiful image is from Itamar Haber, who is the developer advocate in Redis Labs, and who is a just all-around nice guy. He let me borrow the slides. He helped me with my talk, also review it. And this is what he used to explain modules. I think he drew me over there. I just never wear skirts, but OK. So the user, this is how Redis works at the moment. The user connects to the app that instantiates the Redis client, This is the Redis client, this circle. And then the Redis clients issues a request to the server that connects to the core, that connects to the Redis core, that connects to the data on the low level, and then sends everything back to the core server, and sends the value back to the user. So now with modules, this happens. The user connects to the app, connects to the client connects to the module. Now the module connects to the core. This is for the high-level API. The module connects to the core, which connects to the data. And then all the way back, the data is sent to the user. Now with the low-level API, the low-level commands, the client connects to the module, and the module connects directly to the data. It can manipulate data directly on the low level without even taking the data outside of the Redis server, which gives a huge increase in speeds. So let's see a few basic examples, really basic examples. In the high-level API, this is like the only function that is exposed. Redis module call. In it, we are passing the context object, which is like the developer shouldn't know anything about it. It should be opaque to the developer. It contains information about the client state and stuff like that. Then we pass the command, we pass the arguments, and we pass the format specifier. So in this, we're just specifying what is the type of these arguments. S means this, Redis module string is received, and then the null terminated C string pointer. OK. Anatomy of a module. So every module should contain the definitions of the API, the header file in the beginning, and then it should have this function, Redis module onload, which registers the command and the module. So yes, OK. Register the module or error out, register the command or error out. If it returns, no, this is the name of the command that we will be typing in the command line. This is the name of the function that contains the logic of the module. This is that function. Let's zoom in to see what happens in there. So we need, in the beginning, it's customary to first just check if we received exactly the number of arguments we are expecting. Then there is this command, enable automatic memory management for people like me that don't do C. It will just liberate memory. It will release memory and take care of all that low-level stuff that we are usually, as PHP developers even more, we are not used to take care of. Then we define call reply, a call reply object, and then there's the Redis module call command I just explained earlier, which received the Redis command that we want to run, the context, the parameters, the specifier, and then we say that this is how we send the reply back to the user. Reply with call reply. ctext reply, Redis module OK, and this will return the value of this key after it has been increased. And this is pretty basic, but I think we can already see what can be done here. So this is the high-level module. I only have 5 minutes left now. OK. Reply with the call object. Now, the low-level API. In that same method that I just explained here, instead of using that call command, we can go ahead and use the functions for directly accessing the data in Redis. Open key, and we specify that we just want to open it for reading or for writing. We need to define that nicely or in an organized in an organized way. And then we check the type of the key, for example, in this example of ours. And if this key is empty, we set it to the argument we pass to this module, for example. A simple example, but it's good enough for us to see what we can do. So this is happening in Redis memory. So now let's go back to our example. If we could do all the processing, all of those 13 or something, 9 or something network requests that were manipulating data, not just even taking, but manipulating data, adding data to Redis, we could do all of that inside of a module. That doesn't make sense if we are one company that only checks this, periodically. But if we are a company that does that, if our business is analyzing tweets and we have a lot of traffic, a lot of data, then I think that it might make sense to create a module that is going to handle all this. Now, it's worth mentioning, let me just finish here. We close the key, okay, and we finish here. It's worth mentioning that while we are calling a module and also a Lua script, everything else is on hold. Redis is single-threaded, and while it is running one thing, either it's a command, a native command, or it's a call to a Lua script or call to a module, everything else is on hold. So we have to be very careful of the timing of our operations. Compiling, it's the regular way, I guess. As I said, it's not my strong point. And this is how we load this is the compiled module. We got from here. So this is the compiled module. We download the Redis server, and we compile it together with this module. And then we just run the commands like this. If you remember, when we defined the module, we defined the name of the command would be tweet.process. It seems that this is some kind of standard to just have a dot notation, like namespacing, for command names. And then we pass the tweet ID, for example, and the full tweet. And then that's it. From inside of the module, we would be able to access the other keys that were storing the hashtags and the keywords that we are processing. So this is the only thing that we would be passing to the Redis server. And I hope you enjoyed this trip of speeding these things up. I hope you learned something new about Redis. Thank you very much. Thank you.